Hello everyone, I am Priyanka Giri and I am a final year PhD student at University of Pisa, and today I am going to talk about the CO2 mode cleaner being built for the thermal compensation system in Advanced Virgo Plus. To our knowledge, this is the first ever mode cleaner for the CO2 wavelength. The motivation for the mode cleaner comes from the fact that for optimal operation, a good quality beam is required. And for systems such as the gravitational wave detectors, the condition of the beam quality can be even more stringent. Therefore, first I'll talk about the 2G detector, Advanced Virgo, and in specific, I'll be discussing the thermal effects we observe in the Advanced Virgo Plus. Then I'll talk about the motivation required for the mode cleaner in the TCS system, and what are the locking strategy, the demodulation scheme, and the temperature control being implemented for this mode cleaner. So let's first have a look at the Advanced Virgo optical layout, where we have a microsun interferometer consisting two Fabry-Perot cavities, and the condition for in the Fabry-Perot cavities is that the light can only pass through it if the free spectral range frequency is equal to the speed of light divided by the 2L, where L is the arm length. Another thing we have in the Virgo is that we need to use a high input laser power to reduce the short noise. Apart from the Fabry-Perot cavities and the microsun interferometer, we also have two recycling cavities, mainly the power recycling and the signal recycling. These recycling cavities helps us to improve the overall sensitivity of the detectors. Now moving on, for O5, we will be using 80 watts of the input power. And thus, it will also increase the thermal lensing effect in the input test masses. This will, in result, decrease the recycling cavity gains if not compensated. So we compensate these thermal lensing effect using a system called Double Axicon System, or DAS, where you can easily observe the effect which was seen even during the O3 run. So here is the data for the O3, that when the DAS was on, or let's say when you compensated for this thermal lensing effect, you overall see a good power in the sidebands, and your BNS range was also quite nice. However, when your DAS is off, you have a dark port power quite high, and you have a sudden decrease in the sidebands power. Therefore, it's really important to maintain the recycling cavity gains in the interferometer, which is being done by having a nice thermal compensation system. Now, how do we actually compensate for these optical aberrations? So we basically project axisymmetric heating pattern on the compensation plate in the power recycling cavity. These compensation plates are just before the input test masses. So in that case, what we have is, in the axicon system, we have a conical lens which generates two axisymmetric rings. One is the outer ring and one is the inner ring. And this is being projected on the compensation plate, and it being completely absorbed due to the fact that these are being produced using a CO2 laser beam, where we reshape the beam using axicons. So this is a quite high powered laser, it's like 50 watts. And we are reshaping it using these axicon system. So due to this high powered CO2 laser, we also encounter the higher order modes. So what are the effects? Why do we even care? And does it matter to even get rid of it? The answer is yes, because they basically affect the intensity distribution of the DAS ring. So here's an example where if you have, let's say, consider like 75% of TM00, 21% of TM01, and 4% of TM11 mode, you can clearly see that the intensity of the outer ring is quite bad. And for the inner ring, you quite have like a blob shape. This effect of the poor intensity distribution in the rings is being also computed for the O5 used by computing the optical path length increase in the overall interferometer. What we observed from our required condition that we have order of magnitude difference. So henceforth, it's very important to get rid of these higher modes using the mode cleaner. At the moment, we do not require such high power in the DAS Therefore, we are able to use a special filtering, and it reduces about 50% of the power. So for O3 and O4, it was fine, but for O5, when we'll have a high powered in the interferometer, we also require to have higher power using the DAS. So we are building a prototype here of the mode cleaner, and we are going for the triangular cavity because we do not have a Faraday isolator for the CO2 wavelength. And we have already made checks where we saw from the Phoenix simulation that for this cavity, the rejection factor is about the same as the Phoenix, which is 100. And we were mainly interested in the 0, 1 and 1, 1 mode, which we think is there in the laser. And we see there's almost no overlap or very minimum overlap between the fundamental mode and the higher modes after this. So we are quite confident that the rejection factor going to be about 90 to 95%. Now, moving on, the specific of the locking of the mode cleaner will be done with the dithering. Why? Well, normally we use EOM to generate the sidebands and then make the lock using the PDH technique, but there is no EOM available for the CO2 wavelength. So henceforth, what we will do is just that we will simply dither one of the cavity mirror using the piezo driver. Some specific of the cavity is that we will first have the cavity line width of about 5.82 megahertz, the Phoenix of about 103, and the laser line width is around 100 kilohertz. Now with these specifics, we need to have a further check. And the first check that we did was to basically see or understand if it's even possible to have the dither lock for the cavity. For doing that, we had Unbalanced Mach-Zehnder setup built up, where we measured the frequency noise to see if it is much less than the cavity line width at the dithering frequency. So we are going for about 5 to 10 kilohertz of dithering, and we tried to measure, we actually measure the frequency noise in this setup. So at the measurement was done at the mid fringe, and with the arm length difference of about 69 centimeter. And the PSD was taken over the contrast in the power in the two ports. And by taking this overall PSD, we observed the frequency noise measurement. So what we saw that the frequency noise RMS is about 930 kilohertz, which is quite less compared to the cavity line width, which is 5.8 megahertz. And this check basically tells us that the dithering is possible. Now moving on, since we are making the lock using by changing the length of the cavity, we need to make sure that the cavity length does not change given the environmental conditions. So for that, we have implemented a temperature control system using PID and the Peltier Syste. And we observed some good results that for a given geometrical cavity length of about 500 centimeter, we observed only 24 nanometer of change, which is quite nice. So we know that we can have a good temperature control of the cavity and the dithering will not be affected by it. Here are just the plot where we use some PID parameters for the optimal control. And this is the transfer function of the control scheme. To summarize, we saw that what is the significance of the mode cleaner to compensate the thermal lensing for advanced Virgo Plus. We also saw that the temperature control is being already done, and we made the check that the dithering is possible for the CO2 mode cleaner. Now for the future, since we are going to have 5 kilowatt of circulating power in the cavity, we need to understand the thermal load of it. So for doing so, we are currently doing the thermomechanical simulation with the ANSYS. Then we will move on to the cavity lock-in control design with LabVIEW, and then we'll try to make the lock. And after the lock, we'll have the mode matching of the cavity. Thank you.